The first three sheets that I passed out, they kind of look alike, don't they? Part 1, Part 2, Part 3 look very, very similar. This is actually our formal presentation for ice charts. Okay? The ice chart example that we did not too long ago. What you'll notice on Part 1, if you look on the back, you'll see the ice chart, how it's aligned and set up, and we'll do this again with the examples. And there at the bottom, it actually shows the stepwise procedure that I used algebra-wise to solve this problem. Okay, that's one way of doing it. On Part 2, if you look at the back side, look at that equation that's smack dab in the middle. What is that? Part 2. Quadratic equation. Now, you won't need to do the quadratic equation today. We'll talk about it a little bit later on. Today I'm just introducing what's called the 5% rule. And I'll talk about that here in a moment. But the quadratic equation will be given to you. You just have to know how to use it. Okay? So that's what the second part is. The third part is what we will be doing, which is called the 5% rule. Now, the 5% rule does something pretty neat, and I don't think any of you have ever done this before in algebra, but it allows us to make some adjustments to the math while making it much, much faster and still giving us an answer within 5% of the actual value, which is a common practice, especially on the AP exam, when you work out equilibrium problems, that you're not going to have a lot of time to work out quadratic equations, very complicated algebra problems. But using the 5% rule is really going to be beneficial. Okay? So let's go ahead and go to the fourth sheet, Part 4. So those first three are there for information. And let's go right to the example. So I'm going to introduce the 5% rule in the example because me explaining it to you, you're all going to go, what? I know. All right. So let's look at the first example on Part 4. Where it says at 223 degrees Celsius, the equilibrium constant, K, is equal to 4.1 times 10 to the negative 4 for the reaction. And the reaction, and I know you have it on the sheet of paper, but I want to do it for the viewers at home. We have 2NO that decomposes into nitrogen gas and oxygen gas. Okay. The question says, calculate the concentration of all the species at equilibrium for each of the following original mixtures. So in Part A, we're given a 2 moles of pure NO in a 4-liter flask. So is that a concentration or a pressure? It's a concentration. So we are going to do a molarity ice chart. So ice again, what does ice represent?
Initial concentration and change.
All right, the initial concentration or pressure, the change in the concentration or the pressure, and the equilibrium at the concentration, the equilibrium of the concentration and pressures. And we would take the values at equilibrium and plug those into our expression. So let's go ahead, and again, an ice chart is simply used for organizational purposes. So the best way to get organized is by making an ice chart. So let's write down what we know about this. So we have 2 moles in a 4-liter flask. So what's the molarity for that?
2 divided by 4.
Which is?
1/2.
0.5, okay. Now, how much nitrogen and oxygen do we know we have in Part A? Or are we given? We're not given any information, are we?
Exactly.
So if we're not given any information, it's very safe to say we don't have any initially. Okay. Here's my question. Are we at equilibrium?
No.
No, we are not. And which direction will the reaction shift to achieve equilibrium? To the right. So that means that we need to take some NO and make nitrogen and oxygen. So we know we need to shift to the right. Pretty basic. All right, now for the change, we don't know by how much it's changing, but what we are going to do is use variables, in this case x. So how many NOs do we have in the balanced equation? 2. So we'll change it, since we're going from left to right, we're shifting to the right, we're going to say that this changes by a factor of negative 2x. And the coefficients in front of the nitrogen and oxygen each are what? 1. So this will change by a factor of x. But since it's shifting to the right, and again, here's our fence, everything on this side increases while everything on this side decreases because it shifts to the right. Here's our variables for that. All right, and at equilibrium, we'll have a concentration of 0.5 minus 2x, where on this side we'll have x and x. So again, ice charts are used for organizational purposes. Now, what do we do with all this information? Well, we always want to write our expression first. So based on our balanced equation, we'll write the expression, K, and what do you put on top? Products. So we'll put the concentration of the nitrogen on top, and the concentration of the oxygen as well. And then on the bottom, we put our reactants. And since we have a coefficient of 2, that means we square it. Okay? And this is all equal to 4.1 times 10 to the negative 4, I believe. Yeah. So 4.1 times 10 to the negative 4. And that's molarity. All right, so now let's go ahead and plug these values in. And we want to plug the values at equilibrium. So in this case, actually, let's just go to 4.1. So we can say that 4.1 times 10 to the negative 4 is equal to nitrogen, which has a concentration of x, we don't know what it is yet, times the concentration of oxygen at equilibrium, which is x, over 0.5 minus 2x, but what do we need to do to that? Square it. Okay. Now, here's what's really cool about the 5% rule. Let's get back.
Why did you square 0.5?
Why did I square this? Because in the expression we have a square.
And why is the upper one in brackets and the bottom one is in parentheses?
Ask that again. Why is what?
Top one is in brackets. So the top is concentration.
These are concentrations. This is the math. So if you want to do brackets or parentheses, that's fine.
So it doesn't have to do with pressure and concentration.
The expression, this represents concentrations. The parentheses represent pressure for just the expression. But once you start plugging values in, I don't care if you use parentheses or brackets.
Okay, very good.
All right. So here's what the 5% rule allows us to do. This down here would make it for some very fun math, right? Using FOIL, I think it is, where we actually square that all out and everything. I don't know, I don't teach math. But with the 5% rule, whatever we add or subtract x-wise to a given concentration, we drop. Okay? Whatever is added or subtracted to a given concentration, like in this case, we're only given 0.5, we drop the x. So we rewrite it like this. Okay? We drop the x, or in this case, 2x. This is the 5% rule. And in other words, when we solve for x, the x's here, because we weren't given any concentration, so we need to know what those are. When we get an answer for x, I guarantee it's going to be within 5% of the actual value. So once we have this, and we know that's equal to, I'll rewrite that again, 4.1 times 10 to the negative 4, this becomes a much easier algebra problem, right? So if we want to take, and I'm going to move these guys up, so now we're going to go x squared is equal to, what's 0.5 squared? Anybody can do that in their head? That's good. And times 4.1 times 10 to the negative 4, let's get a number there. So 4.1 times 0.4 times 0.25. So I get 1.025 times 10 to the negative 1, 2, 3, 4. Okay. So that's equal to x squared. So how can I get x all by itself?
Square root.
Take the square root. Okay, so we'll take square root of that value. And again, I still have it in my calculator. So square root of answer, and I get 0.0101. Okay. Now the question wants us to give the concentrations for each of these things. Since we used the 5% rule, and you don't have to, trust me, if you want to do the algebra, that's fine. But we solve for x. Since I used the 5% rule, what I don't want to do is take the value that already has a 5% error and plug it back in. What's really neat about this, when we go back and tell everybody what our concentrations are, whatever the concentration that we started with is our concentration at equilibrium, using the 5% rule. And I'll explain why here in a second. And then for nitrogen, actually, and oxygen, is equal to what X is. So whatever X is. If it were 2X, what would we do? Multiply by 2. But it's just X. So 0.0101 molarity. Okay. That's it. Now, does anybody have a graphing calculator that will give you the actual value if you plug this in? Can anybody solve for X? I have a calculator that can do that, but I'm curious if any of you can do it.
So we don't have to plug what we found in for X for,
No, do not.
Okay.
Because what you're doing is you're actually you're taking a value that's not true and you're plugging it back in. So with the 5% rule, whatever the concentration is given, that's what we stick with. And this is how you're going to work out the problems on the AP exam. You will use the 5% rule. Okay? Did anybody get it? Brian, you still working on it?
Yeah.
Come on, buddy, you can
do it. I believe. Exactly.
The answer? Right here. This is what the question was asking. What are the concentrations at equilibrium? So, and this is using the 5% rule.
Why does it stand as 0.5? Because you said it doesn't.
Because if we take this value here and subtract it out, what'd you get?
Would you get two values for it?
Yeah, you should get a negative and a positive. Use only the positive.
The positive 0.00973.
Okay, 0, what?
973.
73?
Yeah.
Pretty darn good. Okay. So this is within 5% of the actual value. And this is a standard practice for the AP exam.
Are you going to let him use that graphing calculator on the test?
If he wants to.
I'm gonna go
But the 5% rule is much easier.
No, I mean to.
Looks like that.
Yeah.
Type in the numbers.
If you know how to do it.
It's hard.
Evidently, Brian's the only one. All right, let's look at the next example. And I believe we're going to keep that same expression. So I'll leave that up there. Except the ice chart's going to look a little different. I think the concentration for the NO is the same. So part B here. All right. B says we had 2 moles of NO in a 4-liter flask. Okay, so that's good. And 1 mole of N2 in a 4-liter flask. So what's my concentration of N2 initially?
Because
1 mole. Oh, 1 divided by 4.
1 divided by 4 is what? 0.25. And oxygen?
0.
0, because we're not given any information. All right. Is this at equilibrium?
No.
No, because we have a 0. So which direction will this shift? To the right. So what that means is this side will be reduced, this side will increase. Same thing, whatever your coefficient is, that's by what factor we're going to do it by. So plus x, and then down here at equilibrium we'll have 0.5 minus 2x. Here we have 0.25 plus x, and then x. Now, this makes for a very fun algebra problem. So we can plug in our values here. Let's go ahead and do that. So we have 0.25 plus x times x divided by 0.5 minus 2x squared, and that all equals 4.1 times 10 to the negative 4. Okay? Now that is a fun looking algebra problem. Right? However, with the 5% rule, any x's that are added or subtracted from a given concentration, you may drop. However, if you do that, put this on the other side, you have to show this first. Okay? Got to show this first if you're going to use 5% rule. So what that now changes into is 0.25 times x over 0.5 squared, which is still equal to 4.1 times 10 to the negative 4. Okay.
You drop both the x's. Oh,
You
yeah,
drop
so-
any x that's added to or subtracted
Okay,
from.
Okay.
Now, I don't need a calculator to solve for this one. Because what is 0.5 squared again?
0.25.
0.25. So you've got 0.25 times x over 0.25. So x is equal to 4.1 times 10 to the negative 4.
Wait, what step did you say in the shelf you're going to drop the x's?
From here. From here to here. This is what it actually is. This is what the 5% rule.
Okay.
Okay. So x in this case is 4.1 times 10 to the negative 4. And I'd be very curious to see what that value really is by doing this. And this probably would take most of us at least, on average, 30 minutes to solve, rearranging and doing all that fun stuff. 5% rule, 30 seconds.
I don't think it would take 35 minutes.
Yeah? I'd like to see you set it up.
All right, I'll start right now.
All right, so giving our final concentrations. So NO, since we started with 0.5, we're going to finish with 0.5. The nitrogen is 0.25. And then our oxygen is 4.1 times 10 negative 4.
Slow down, Jeff Gordon. Wait a minute.
Okay.
Yeah, never mind.
So again, the concentrations that we started with, as long as we're using the 5% rule. Now, if we're using the quadratic equation and we found out what x was, then we'd either add it or subtract from it.
We should have learned this first. This is a lot easier. This is easy. I understand this.
Yeah.
It's ice charts.
Well, it's about the same as
Yeah.
like I feel like it's the same, but it's easy to mess up this one.
Questions on
They're
that?
all easy. They're all easy to mess up.
Oh, we got one more example.
We got one more.
An excellent.
But anybody actually find out what the real x is? I don't want to pick on Brian.
2.9 times.
What? Somebody just mumbling back there.
I made up one.
All right. Let's look at the example on the back. Actually, go ahead and try that while I'm cleaning the board. I'll give you guys a head start.
You just drop if there's adding an x or subtracting an x.
And I think it says something along the lines of this would make a great AP exam question, test question, or quiz question. And I would even go so far as to put this on the portion where you don't get to use a calculator.
Why?
Yeah.
Why would you be that guy?
You don't need a calculator for this, so put your calculator away. You don't need it for this one.
I got devoted to do so good. What are you arguing?
All right. And so we'll put the ice chart up.
No, I meant not. 0.025.
Okay.
No.
All right. So here's the question. I'll read it aloud since most of you have already started on it. Number 2, it says an excellent AP exam quiz or test question. Well, we've already taken the quiz, so it's going to be a test question. 345 degrees Celsius, the K, or the equilibrium constant for this reaction is 1.3 times 10 to the negative 6, where we have this, the calcium oxide decomposes into calcium carbonate decomposes into calcium oxide and carbon dioxide. It wants you to calculate the concentrations of all the species at equilibrium. And then it says on here, hint, you don't need to use the 5% rule. Okay? Yeah,
So the temperature, we don't even need the temperature in this, do we?
correct. You can ignore the temperature.
Okay.
Okay? All right, so how do we start this? What do we know?
The initial values are all 0.
You know what?
The initial values are all 0.
The initial volume for all are
The
0?
Initial values are all 0. Initial.
We can't have zeros on both sides. That's a no-no.
We know K equals 1 point.
We do know the equilibrium constant. What else do we know? It will be here.
Don't use the 5% rule.
Don't use 5% rule. Yeah, Brian?
Wouldn't CO2 be the only gas, or does that matter?
Oh, it matters.
Alright.
It matters a lot.
Alright.
So, what values do we put here for these solids?
X.
Don't put 0 because 0 implies that it can change. So for solids and liquids, we put a dash. Put a dash. Dash means this isn't changing. Also, the dash means it's not going to show up in the expression. And you put it in the expression, we got issues. All right. So how much carbon dioxide do we start with?
0.
0. Very good. So we don't have any. You like that?
Not really.
So what does the calcium carbonate and calcium oxide change by?
0.
Not by 0. Dash.
Oh my goodness.
And what does carbon dioxide change by?
0.
No.
Dash. Dash.
2 dash.
X plus or minus?
2 dash.
X.
Plus. Now, hang on. Shh. So what this is saying is, since I don't have any information about carbon dioxide, we know this reaction must shift to the right, because we don't have any. So we've got to take some solid and make it into a gas. Okay? All right. And then at equilibrium, what's our concentrations for these guys?
Dash.
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 Slash.
Dash.
And X. Okay.
So,
All right. So here's our ice chart. And again, ice charts are used for organizational purposes. Let's now write the equilibrium expression. So K is equal to what?
X.
And we're looking for what? Concentration or, yeah, concentration, so it'll be brackets.
Equals X.
No, expression first.
Oh, it's
Oh.
CaO times CO.
Yeah, you want to put that in there?
Oh crap, CO2.
Thank you. So CO2
Times.
Divided by
times,
1. Oh, times. You can't put that in because it's.
Oh, we're not supposed to put dashes in.
don't put dashes in.
Don't put anything.
So
Times
you can
1.
put an equal sign, right?
Okay.
Do we know the constant for or the value?
1.3 times 10 to the negative 6.
1.3 times 10 to the negative 6. Okay, so now that we have our carbon dioxide expression, and let's solve for X.
Oh, we sure we just did.
Yeah.
That was stupid.
Do I have to
So,
what?
did you figure this one out?
I guess so.
Yeah, that's your expression right there.
You so go over here.
I'm
Okay.
joking. I got it. He's lying.
Now, here's another thing. Don't freak out and go, look at all the space he gave us.
That means there's a lot of work.
I used all my space.
You used all good.
Is that it?
That's it.